Okay, well, we're 2 minutes past, so I guess that means we might as well start. If anybody else trickles in, they'll get cut up. So I'm excited for our next talk. In fact, our next two talks are going to be thematically very similar, intentionally one after the other. The first one, we have Stan Polu from OpenAI, who's telling us about GPT-f. So can we use language models for proving theorems? So Stan, thank you for coming.
Thank you very much. Cool. So I'm going to be presenting the results from a paper we published. We posted on arXiv a couple months ago, done with Yes, it's Cover at OpenAI, and it talks about generative language modeling for automated theorem proving. So GPT-f explores the application of transformer-based language models to automated theorem proving. So you may ask, what is a transformer-based language model, obviously? And so a transformer-based language model is a neural network that tries to generate text. And so you might ask, what is a neural network? And so a neural network is basically a very large circuit whose weights are parameterizable, and you kind of change the weights based on gradient descent. So basically you have a ton of examples. That are shaped X with Y, and you predict by computing through the network the prediction Y for a given X gives you a distribution over the distribution of the various Ys, and you can compute a loss, and you backtrack that loss through the network to update the weights. And at the end of the training, it gives you a very large circuit, which is basically a function that mimics or fits the conditional probability of Y given X. And so that applied to language modeling is slightly more elaborate in the sense that it's autoregressive, meaning that given a sequence of tokens, which is basically text, you can think of them as words or letters, you try to infer the next token, right? And once you've done that, you add that to your what we call the context, which is the condition, the text condition on your prediction, and you keep re-inferring a next token, and you keep going like that. And it gives you a system that, given no context at all, will generate some text, or given a fixed context, will try to autocomplete the text. So that's really basically what's at work if you use Gmail and you have those autocompletes. It's a system similar to that. And so it's interesting because we believe for theorem proving, because it has the capability to generate original mathematical terms, which is somewhat lacking from conventional ATPs. If you have an existential proof, sometimes you want to generate a witness, and it's pretty hard to find a witness by just a pure algorithm. Here we have an opportunity to do so by training on the right data, the right model. Why it interests us at OpenAI, it's because formal math is reasoning complete, in the sense that any advance in formal math is definitely an advance in terms of reasoning. And more importantly, it's amenable to search and therefore allows data generation. So language models, so we like to train very large language models at OpenAI, and language models are reputed for doing those crazy completions. So if you train a big language model on the entire internet, you give it some text and it'll complete the text in a way that is pretty sensible. But they're also very well known for doing silly mistakes. So they're very good at predicting stuff, but they're very bad at verifying their predictions. So as an example, if you ask GPT-3, the very large language model that we've released through an API, if you ask something like, I have 3 apples on the plate, I give 1 apple to Mark gives 1 apple to Paul puts back an apple on the plate, it will probably don't know, or not going to be able to answer the question how many apples are on the plate. And so we're very interested into that reasoning aspect that is lacking the current language models, and that's why applying it to formal math is interesting. And if you think about generally in machine learning these days, outside of games such as chess and Go, where we've seen tremendous results from DeepMind, obviously, the data sets that we have access to for reasoning tasks are pretty scarce and they're pretty small. So it's a very interesting opportunity for us to use a formal math, because since we have a verifier, we can check our predictions. And if a prediction gets checked, it becomes fresh data, right? So it's new data that we can train on. Cool. And so finally, the early intuition is the following. As I mentioned, like a language model is really bad, really good at predicting stuff, but really bad at checking that prediction. And on the contrary, formal systems are really good at checking stuff, but really bad at generating new stuff. So it's really an attempt at putting them together and see what comes out of that. So we've been using Metamath for our initial experiments. I'm gonna go through Metamath really quickly and explain why we picked it, and then follow. So Metamath has a bunch of advantages. It's super fast. It's simple. It's very simple. It has a quite large enough database of theorems, and more importantly, it is super straightforward to extract a clean data set of, given a goal, what is the proof step to apply, and what are the new sub goals that you get out of them. So let's walk through a very trivial Metamath example. So let me try to have a pointer. You probably can see my pointer now. So if we have a goal which tries to prove 3 + 2 = 5, you're gonna, oops, sorry. What's gonna happen is that in Metamath, you have only one tactic, which consists in providing a statement that has been previously proven, a theorem, and providing substitutions for the variables that appear in that theorem in such a way that the conclusion of the theorem unifies to the current goal. And after applying the substitutions, the hypothesis of the theorem becomes the new subgoals. So here we want to prove 3 + 2 = 5. So A has to be substituted with 3 + 2, which is here. C has to be substituted with 5, which is here. And we're using the equality transitivity here. And so we have a B that is completely unbound and free. So it's interesting because right there, to make progress, you have to generate a new term that comes somewhat out of nowhere. And so here we're going to use B substitute with 4 + 1. It gets us 2 new subgoals. A = B gets turned into 3 + 2 = 4 + 1. C = B gets turned into 5 = 4 + 1. As it happens, 5 = 4 + 1 is the definitions of 5 in Metamath. And so we just apply that definition. There is no hypothesis, so that branch is complete. And finally, we keep going with new proof steps in that way. So Metamath being that simple, it's really convenient for machine learning integration because you can really test a bunch of stuff. But it also has a bunch of disadvantages. The main one is that there is no high-level tactics and very little amount of automation. And so it makes it a very DIY system. And to some extent, I guess it's a supposition prevents broad usage in a sense that you guys are not using Metamath today, you're using me. So that's definitely a disadvantage. Awesome. So the dataset that we extracted from Metamath is exactly that. We extracted a very large JSON lines file that contains stats. So a proof label is the label of the theorem from whose proof we extracted those goals and proof steps. And for all the goals and proof steps traversed, we record the goal and the proof step. The proof step is, again, the theorems that we use, presented as its type, if we're thinking in type theory, the statement here, and the substitutions that were applied. We also record the tree structure with some hashes, pretty straightforwardly. It gives us a train set and a valid and a test set. We generally have a valid and a test set in machine learning. You do your experimentation and your iteration with the valid sets. And at the end of your kind of project, you do a final check on the test sets and report those numbers. So we have 36K theorems on the train set, which represents 3 million proof steps, and 1K theorems and 90K proof steps for both the valid and the test sets. Awesome. So what is the training objective that we use? As I explained, language models is really a system. You give a query or context, and it'll autocomplete the rest. And so we very straightforwardly train on that. We have a goal magic keyword. We inject, that's pure text, right? We inject the goal statement here. Then we have a proof step keyword that tells the model, hey, it's time to generate a proof step. And then we train on the generation of that proof step, which is the theorem statements and the substitutions as text, exactly as represented here. There's really no magic at all. It's just a kind of fancy autocomplete train on Metamath. And so how does proof search works? With just that train model, we can already generate proofs. And this is how it works. We basically take the root goal, and we generate the context consisting of goal, the goal statement, and proof steps. And we generate a bunch of tactics of proof steps from the model. And we'll do something like 32 expansions. If the model is very confident about its prediction, most of them will collapse on a couple predictions. If the model is pretty lost, we'll have 32 different tactics. Then we submit that to a Metamath verifier. The Metamath verifier selects the ones that are syntactically correct and that correctly unifies to the top goal. And it gives us a set of new sub-goals. And from there, we just need to expand those new sub-goals and keep going until we've closed all the branches, right? Or at least we have a subtree in that hypertree that is closed. And the way we prioritize that search, we could do breadth first search or depth first search. But the way we prioritize that is we use an extra signal from the model to prioritize that search, which is what we call the cumulative log prob of the generation. And the cumulative log prob of the generation is the sum of the log of the probability of the tokens that are in the generation. So every time we generate a new token, it comes with, it's sampled from a probability distribution over all possible tokens, let's say the alphabet. And so we take that probability, we take the log of that probability, and we sum those probabilities. So this kind of represents how confident the model is in its prediction. And so it's an interesting signal from the model about how confident it was in the prediction it made. So we really push those goals in a cumulative log prob prioritized queue, and we pull those goals from there and keep expanding those. And at each iteration, we try to check the entire proof tree, and if we find the proof, we're pretty much done. So this is basically the gist of how we apply generative language modeling to formal math, and how it enables us to generate proof. And so let's see kind of some results that we got. So we trained various model sizes. So model sizes are actually pretty important. Generally, there's a shared belief that the bigger the model, the better it will get, because actually it has more computes available both at training and evaluation, because there's more weights involved, so more matrix multiplication involved, and so there's more computation happening, and so it'll make better prediction in general. And so we trained a first 160 million parameters language model from scratch and achieve a 28.96 performance. So 28% performance means that out of our valid sets, we sample proof from the statements that are in there. We don't have access to the proof in the valid set. We just have the statements. We sample proof using the technique that I described before, and we're able to close 28% of those doing that using the proof search that I described before. No, there is some kind of a magic happening that you can use, is that you can use something that we call pre-training. And so pre-training is the simple idea that when you have a data set that is pretty scarce, what you can do is find another data set that is pretty big, and you train on that data set first. And finally, you take your model train and you retrain on this data set that you're interested in. And for some reasons, that's the way the universe is made, there is some form of effective transfer from one data set to the other. So the pre-training that we've tried are the following. If we take common crawl, so common crawl is basically, you can think of that as a crawl of the internet. And so we pre-train our models on the internet, on the text on the internet, and then we fine-tune on Metamath, and we get a 4% bump. That's pretty mesmerizing because there's not a lot of formal math on the internet, right? But yet you get an interesting bump. It's probably because the pre-training made emerge some features in the model, in the weights of the model, that are useful eventually to formal math. And they might be just purely syntactic, they might be slightly higher level. It's very hard to introspect those, but the results tells us that there is some transfer. We then we then tried pre-training on GitHub, the Python code from GitHub, and get an extra 1% compared to common crawl. And finally, the best result came from what we call webmath, which is kind of a mixed bag of stuff related to math. So it's 30% Python GitHub, 30% Math Stack Exchange, 30% archive maths, 6% Math Overflow because it's not big, 1% plant math because it's not big as well. And so we take that bunch of data that is math related, completely informal in its shape. We pre-train on that, and then we fine tune on the Metamath dataset that I described before. And we get up to 34.79%. And I think the interesting bits here is the massive bump that we get from nothing to pre-training on the internet. And the other interesting one is the bump that we get from GitHub to webmath, because one could say that all we get from training is kind of syntactic features that are useful in a sense, but not really math related. The fact that we get a non-negligible bump from using webmath instead of GitHub kind of gives us a hint that there is some effective math related transfer happening between the pre-training and the fine-tuning, which is kind of exciting because there is obviously much more informal math information on the internet than formal math information. So that's something that we can leverage. That being said, the bump is not that big either. So there is also other techniques that might trump that. All right, and so then we scale the, yeah, good.
Can I briefly ask a question?
Of course.
So does the order in which you do these bumps matter? Like if you first train on webmath and then on GitHub, would that lead to different results?
Yeah, so actually because we have pre-trained model available internally, the webmath pre-trained model is actually before that pre-trained on common crawl. So we have scratched common crawl webmath, and the GitHub model was pre-trained on common crawl as well. So we have common crawl GitHub. So that bump is really significant, that one as well. The comparison here, it must be higher in a sense, unless we do something really wrong, because we take that pre-trained model and kind of re-pre-training on GitHub and re-pre-training on webmath. We've tried, there is obviously some effect of the ordering of the pre-training you use, but they are generally pretty small. One way to think about it is that there is a lot of information on the internet. So you can train on common crawl for most model sizes, definitely for those model sizes. You can train for a long time. So that means that you're pouring compute inside your model, right? And so having that opportunity to pour compute in the model that is somewhat useful is interesting. And then webmath is somewhat smaller. So you cannot pre-train for that much longer on webmath, but you can still pre-train for longer on webmath than you do on Metamath. So you're able to squeeze in more compute that is more math specific before going to Metamath. And so it's probably the case that doing common crawl GitHub webmath would give us a slightly better result. It might also be the case that those things are generally quite destructive. So it might be the case that there's no difference. It's hard to say. So there's not a lot of impact. It's just the intuition is like how much useful compute you're capable to burn into your weights, right? That makes sense?
Yeah, thanks a lot for the extensive answer.
Yeah, no problem. And so here we study the impact of model size. So going from 160 million parameters to 700 million parameters, we get a nice shift. So 28 to 31, and for webmath 34 to 42, which is really non-negligible. It's number of proof that we're capable of closing from the valid sets. All right, so perplexity is basically a measure of the loss that you get at training. So you see that it varies quite not extensively. It's very small perplexity loss leads in pretty high performance gains. And finally, one interesting thing is the number of tokens here column. The number of tokens is the number of tokens we've been training on Metamath for each of those models. So larger models have more capacity, so they tend to overfit faster. Overfitting is when, sorry, I'm trying to unpack every definition as I go so that everybody has all the tools they need to understand. But overfitting happens when you train on the training sets and you keep training. And at some point, you start fitting the training sets too much in a way that it doesn't generalize anymore to the valid sets. And so your test loss, your valid loss it goes down as you train on the training sets because it generalizes in a way that is interesting. And eventually, if you keep training, it starts overfitting the training sets, and your test loss the training loss keeps going down, and the test loss starts going back up. That's what we call overfitting. And so we stop the training at the point of minimal test loss. So that's called early stop. And one interesting thing is that we early stop for all of those models to a much larger number of tokens than the dataset size. The dataset size here is 6 billion tokens. And it's generally speaking, generally happens when there is some amount of reasoning happening in the datasets or required for the dataset. So if you train on a very small version of command crawl, you're going to be overfitting generally at one epoch. One epoch means one pass over the datasets. After you keep going for a second pass, it starts overfitting. So here we're kind of able to go for 3 epochs on the dataset before overfitting, which is interesting. Awesome. And finally, the previous state of the art was in terms of deep learning. Though there is no hammer or whatnot in Metamath. So that was kind of the previous setup for Metamath was a system called MetaGen which was able to achieve 21% performance. So we were kind of glad to double that using transformers. That's kind of the early setup. We kind of said, hey, let's try to use transformers for formal math. Maybe they're not even capable of generating something remotely syntactically correct. Went from that to, they seem to generate things that pass the Metamath parser. That's cool. To, we're capable to close some proof. To, we're capable to double the SOTA. That's cool. Awesome. So the next thing that we did is the following. Basically, we generate as we sample proof. We obviously make the models make mistakes, right? They explore goals that are not useful. They're not able to close proofs, obviously, 60% of the time. But even when you close a proof, you've been exploring a bunch of goals that never got proved and never participated in the final proof, right? And so it's an opportunity it's a signal that we have an opportunity to learn from, right? And so what we did is that once we trained those models, we sampled proofs from the training sets. And the model doesn't achieve 100% accuracy on the training sets because we early stop. So it's something that's generally higher than on the valid set, but it's not that much higher. And we take those proofs and they're closed. So you have a subtree that is the proof. And you have a bunch of other goals that were explored. And so we have an opportunity to label the goals as being useful and not useful, or provable and not non-provable. We keep the ones that were closed inside the proof search. This is the ones that were left open. And we basically introduce a new training objective, which tries to predict whether a goal will be useful to the proof or not. And we do so by a new keyword in our context, which is called outcome. And outcome comes after we just have one label, which is negative or positive, one letter, one token, so N or P. And we can use that to infer a value function. So a value function is something that will value the goal and gives us an indication of how useful it is to the proof. To do so, we train on those labels, right? And then at proof search, for every goal, we do that generation N or P. Once the model is trained, it knows that after outcome, it can only ever be N or P, right? So after being trained, the probability of P is generally equal to 1 minus the probability of N modulo a very small epsilon. And so this gives us a probability estimate for that goal. So this is a function that depends on the weights of the network, and given that goal gives us a probability estimate. And we infer from that a very straightforward value function for the goal, which is the product of the probability of all the siblings of the goals, including itself. So basically, as we apply a tactic, it generates a bunch of new sub-goals, sometimes 0, sometimes 1, sometimes n. And we take the product of the probability of those goals as a value function for all those goals together. And what it gives us a way to prioritize the proof search in a much more interesting way. Why it's more interesting is because the model has an opportunity, by being trained on samples that it generated, to learn from its mistakes. And so doing so, we get the following results. So I'll focus on the 700 million model, pre-trained on WebMath. So this is the 42.5% that was reported before. And one iteration here is what I just described. It means that we generate proof from the trained model, from the training sets. We tag the goals for the proof that were closed, whether they were useful or not. We don't use the goals from the proof that were not closed because they're all tagged negatively. And so there's a good chance that we will be tagging good data negatively. And we retrain the model from scratch on both the first objective and the second objective. So the proof step objective and the outcome objective. And we use the outcome objective to guide proof search. And here it gives us that number, 44%, so, which is a nice boost. And even more interestingly is that we can iterate that process even further. And that iteration gives us 47%. And we also did internally, we don't report that in the paper, but we also did more iteration. And it's kind of as you generate more data, it kind of scales in a somewhat predictable way. So that's what we called expert iteration, the process of using a model, sampling stuff from it and learning from its own sample. That's called expert iteration. And what we use is a learn value function because we kind of learn it from those labels. And so this is the result we got from there. So 47% starts being quite interesting. It means that 1 out of 2 proof in Metamath we can close with proof search, which is nice. Awesome. So that's for the learn value function and the expert iteration. Another result that we report, and that is interesting to keep in mind, I think, and that could be useful to the community in general, is that there is a very big dependence on the amount of compute you use at test time. So a way to test that is the number of attempts we do for each statement in the valid set. So for every numbers that I reported before, we use two attempts, meaning that every theorem in the valid set, we try to sample a proof search using the mechanism that I described twice, and it gives us that performance. And if we increase that number 4, 8, 16, 32, we see a kind of a dramatic increase in performance, right? And for the ones among you that can plot power laws in their head, that's actually what it looks like. We do love power laws because there is many stuff related to large language models that eventually get fitted to a power law. And unfortunately here we see that it bends. We kind of expected it to go
I think it's not just me that has lost STEM. Is that true?
No, it's lost for me as well.
Well, yeah.
Unfortunately, this is the way of the Zoom workshop, I think.
Indeed.
Maybe you got
Okay,
overfit.
opinion on Zulip?
Trained too much and he got overfitted.
I do not see him active on the Zulip. Hopefully he'll be back in a second. In the meantime, I will add to his nice presentation that if you're looking for some entertainment, you should look at the paper that is connected. It's a really nice paper. It's very fun to read, I think. It's worth taking the time. See in the chat, do I have a link? It's this. Yes, I posted a link to the paper in the chat. We're not too pressed on time in this session. Stan told me he would take a little less time than we had budgeted for him. Jason and Jesse, who are going next, and also talking about GPT-related things, they can take extra time, but they're not ready at the moment. We obviously don't want to assume that Stan is not coming back yet. But my point is we have some leeway here. Mario, are you here, and have you tried out the Metamath GPT activity?
I'm back. Sorry, where did I drop?
Oh, Stan is here.
I'm so sorry. My internet seems to have fluctuated a little bit. Where did I drop?
We're discussing the curve with the disappointing.
Okay, gotcha. Cool. I was afraid that I dropped much earlier. Let me share my screen again. So sorry about that.
Oh, don't worry.
It's fine.
All right, so going.
That was
the slide
probably
before
the
this.
previous slide. No.
Yes, this one.
Yes.
Right.
Yes.
Yeah. Oh, cool.
Can I interject a very quick question?
Yeah, sure. Good.
Before you get back into swing of things, how long, like order of magnitude, does one attempt take?
1 hour, 1 GPU hour.
Okay, one attempt is 1 GPU hour. Got
it. Right. So I was probably saying that you scale the number of attempts. I hope I defined attempts. And so you scale the number of attempts, and you have a dramatic increase in performance. And if for the ones that can plot power laws in their heads, that's kind of what it looks like. We generally try to fit things to power laws, because when it comes to machine learning, there's a lot of things that fits with power laws in function of compute. And we see that kind of bend at the end, which is kind of sad. You have to bend eventually as you reach 100% accuracy, obviously, but we were expecting to have a more straighter line. And anyway, I think one tidbit that you can keep and that could be useful in general when it comes to machine learning is there's a very it's very often the matter that it's how much compute you were able to pour in your training and how much compute you're able to pour in your test time evaluations. As generally most of the things scale in function of that compute. So it's always interesting to have an opportunity to put more compute in places. Cool. So from those results, we shared some of our work with the Metamath community. The Metamath community cares a lot about short proof, and so what we did is that we took our trained model and sample proof from all the statements in Metamath and shared back the short proof that we found that we're not using more axioms. And it was very, very nicely received by the community. I really like that comment. The shorter proof of int_ss is easier to translate. It's more symmetric in that it treats A and B identically. It's philosophically more concise in that it doesn't rely on the existence of a universal class of all sets. I think when we see a feedback like that, we're very, very pleased, because it's always until we use a benchmark that we can relate to as humans. I mean, some obviously MetaMath experts can relate to the proof we generate. We're starting to be MetaMath beginners or wannabe experts, but it's very hard to relate to the capabilities of the models when we see proofs. And so having somebody share that means that the models were capable to generate some interesting knowledge, which is what matters to us, obviously. If we look at IntSS, we can see proof shortened by OpenAI, and we can see the original proof here. I mean, it's shorter for sure. How much shorter? I don't know. But we were able to find dramatically shorter proof as well, which was really, really neat. And we also built a proof assistant that I'll probably try to show before the end of the talk, which lets you really play with the model and assist you as you build a MetaMath proof. One thing for sure is that proof assistant has been incredibly useful to us, given that we don't have the entire MetaMath SetMM database in our head. It's really useful to have the model generate some proof steps. Sometimes it makes mistakes, obviously, but it generally gives you a hint of the statements that you want, the theorem that you want to use. And so it really enabled us to formalize a bunch of problems much more rapidly. And even more exciting, we had a kind of a 14-year-old French student that say, hey, I'd like to get access to the MetaMath proof assistant that you made. We give him access, and a couple hours after, he came back saying that he was able to test it on a formula that he had to prove for his 11th grade math class the next day, and the model was able to get it right. So that's great. Not sure about the face of their professor when he shared his formalized proof in MetaMath the next day, but I think it's exciting. Cool. So because we have a little bit of time, this is an example proof that we generated. I want to focus on the first proof step, which is here. So the proof is really trivial, but it really shows why we were excited about transformers. So here we're trying to prove that given an integer n, and the fact that n+1 divided by 2 is also an integer, then there must exist a m that is also an integer such that n is equal to 2 times n+1. And when we look at the proof step that was generated by the model, it uses kind of a first order logic theorem to decompose that in multiple steps. And the interesting one is obviously this one here, which is, so pH is the hypothesis that we have here, such that n is an integer and n+1/2 is an integer. So it's reported here so that it unifies in the goals here. And it generates a new, it says, I want to prove a new proof step, a new goal, which is pH in place ch. And ch says, then that implies that n is equal to 2 times n-1 divided by 2 plus 1. And so that's interesting, I think, because the model generated that term entirely on itself. And so that's really the witness that we're looking for, that's m. And the fact that the model is capable of generating the witness is the hard part of that proof. The rest is just gluing stuff together. And so this is really the promise I find of using generative language models, because they're capable of, as an example for existential proof, generate some witness that are kind of exogenous of the goals that you have. Other project that we're working on is Mini F2F is kind of a first step towards the IMO Grand Challenge. It's a small benchmark. I mean, a benchmark of AMC 10 and 12 and easy IMO's problems that we're working on. Our goal is to have that in as many formal language as possible. We're targeting MetaMath and Lean. We really don't want to turn that into a competition, but more into a benchmark that the community of machine learning researchers that are excited about formal math can use to benchmark their systems. Because today, having a numbers on a split of the MetaMath database doesn't mean much. Seeing an increase means something. So going from 21% to 56% definitely shows that there is progress, right? But when you look at that 56%, you don't really understand the capability of the system, because these are lemmas that have been engineered by humans to cut their proof in ways that are convenient to them. So there is a lot of thinking that was put into the design of those lemmas, and all that is not, the model doesn't do that. We just give it the lemmas and it tries to generate a proof, and they're generally short because humans don't like long proof because they're hard to read. And so there's a lot of assistance coming from the mere fact that we're using a split of the database. And so it's very hard to relate in terms of numbers to capabilities. So increase is good, but an absolute numbers really doesn't mean much. So if we build a kind of a small benchmark of AMC 1012, these are very easy problems, right? I haven't done that much math in my life, but I can solve most of them. So I consider them easy. And so I think it's a really great benchmark because we'll all be, as mere humans, capable of relating to the performance of the model on such benchmark. So how it started, we started at 0% close rates on mini F2F. As of today, we are still at 0%. So that proves more challenging than we thought. But I think we see the light at the end of the tunnel, and we should be able to close a few statements from AMC problems soon. It's a challenge because at the end of the day, as I described, we're really fitting a distribution, and today we're fitting the distribution of set.mm in Metamath, and there's not much exercise like that in Metamath. It's mostly formalization of theorems. We all after creating big libraries of theorems, and there's not much examples in there. There's not much exercise. So if you want to have a model capable of being performant on those, you can hope that you generalize to them from the libraries, but it's merely an hope, and you really have to work hard towards shifting the distribution towards there. And so we're doing a bunch of stuff around that. We've demonstrated that there is a curriculum effect. As an example, if you give statements that are out of reach of the model, and you start giving easier statements, and you start being within reach, then generally, as you do those expert iteration loops, the model is capable of climbing that curriculum on itself, meaning that it closes the first statement, uses that proof as a training data, and then start closing more complex statements and keep climbing that curriculum. We've demonstrated that curriculum effect on toy problems very clearly, and our hope is to be able to kind of manually engineer a curriculum for the models towards AMC problems, and eventually IMOs, obviously. So that's kind of what we've been working on, and obviously we've also we're super excited about Lean, and we've started working on Lean, and that's really the core of the next presentation. So I won't say anything about it, but it's going to be awesome. So you should stick around, and so that's pretty much all I have. Since I have a few minutes left, we can also obviously have questions, and we can. I mean, you tell me. You tell me. Do you want to go for questions, and I can also demonstrate the proof assistance really quickly to give a sense of how it works and how it's helpful for formalizing stuff in Metamath.
I'd love to see a very quick demo.
Yeah, sure.
Yeah.
Let's go for it. All right. So this is a very easy proof. If you don't know anything about Metamath, you should be able to at least read it. So it is in deduction form, so that's the reason why you have the fee imply at the beginning, but we don't really care about that. And so we have as a hypothesis here that A, B, and C are complex numbers, and that you have A plus B plus C equal B plus A plus C. So it's
the E dot is element of, is that?
Yes. And so it's an assistivity theorem with a small trick by, I mean, we add commutativity here, right? Because we switch the things around a little bit. Anyway, so we can ask the model to generate a completion for that. So this is going through the API and coming back. And here we can see that there is two completions. There's one that kind of reshaped the statement by not using hypothesis, but using an implication. And there's another one that says, oh, I'm gonna, instead of proving that, I'm gonna prove A plus B plus C equal B plus A plus C, and B plus A plus C equal B plus A plus C, which seems to be kind of a nice step forward, right? So I can, as a human, I can remove this one and select this one. So what the model generated is here, this is the statement, so it's using equality transitivity, and it generated, so A and C are obviously generated because it unifies to the goal, and it generated that B plus A plus C, right? And so I didn't have here to remember, if I don't remember how to use transitivity of equality in that deduction form, the model kind of hinted that for me. Even if it got it wrong, I could have just used that. Now that I have the statement, I could have provided different substitutions that were more useful to me. So the completion here are the following. It tries to commute the equality or just simply eliminate the C here, right? So we want to eliminate the C, definitely. We're left with this one, which should be pretty easy. Don't need to remember anything, just generates the statement for me. And we can ask to check the things that were proved, and we have that goal that was proved. And it goes pretty much the same way here. It finds a statement, a theorem for that directly. So here we can check the proof, and it generates the Metamath statement that is ready to be committed. And not exactly ready, but ready to be used with Metamath. There is another thing that we can do, which is the following. Let me refresh the page. We can also say, hey, I want to use that theorem, and it's going to generate the substitutions that I mean, it's really like a regular proof system. It's going to generate the substitution that unifies the goal, and maybe based on that example here, maybe that the substitution that was used was not really good, and I can provide another one if needed. But anyway, we have a proof here. Slightly more interesting, but nonetheless still trivial. This one is kind of a trivial inequality, square-based inequality. And so it's interesting because the model will have to pattern match the fact that there is a binomial in there. So if we're asking for a completion, it's doing what it's trying to do. So here, it's trying to say that this is equal to that, which is obviously, oh no, it's actually true, but not very useful. And it's also moving the term to the other side of the inequality, which seems interesting because we want to pattern match a binomial. So we've left to proving that 0 is smaller than that expression, which is easy to see. And also that these two things are equivalent, which should be somewhere in the Metamath database because it's obviously just moving a term around an inequality. And so it uses that theorem, which is here. If A and B are reals, then if 0 is smaller than A minus B, then B is smaller than A, pretty obvious. And we're left with proving some the fact that those expressions belong to our reals, which are generally pretty obvious. So it's just using a theorem that said that the addition of two reals are reals. Here we have the square of reals are reals. So this is A is real, A square is real. This one is another one that we don't need. We can remove it. We can check what is proved. All of this got proved. We're left with proving the belonging to R for those ones. It's all pretty trivial. So I'm really just pushing enter every time, right? And pushing Control U to check things. Okay, and we're done with that equivalence. And now we need to, the model needs to pattern match the binomial here. And so that's what it does on the next proof step. So that one is really interesting because, I mean, it's obviously obvious, but if you look at the theorem statement it's using, it's just using that if you have a relationship between A and C, and you have B equals C, then you have that relationship between A and B, and it entirely generates the I minus B square exogenously, right? So it's not something that you can come to by algorithmically looking for it. And so from there, this one is pretty obvious because it's obviously a theorem in Metamath that the square of something is positive. Left to prove that A minus B is positive, generates that statement, why not? And we're done. And finally, this one is just shuffling around the terms a little bit because the binomial. So what it has a good knowledge of the format of every theorem. When you have that thing in Metamath, you still have to shuffle terms around so that it pattern match this theorem that you're going for. And so that's probably what it's doing here. I'm kind of reading quickly, but it looks correct. It's proving that So proving this one is actually going for that theorem, which is the actual format in which the binomial formula is expressed in Metamath. So once we go for this one, we'll see the theorem just pop up, binom to sub. We have to prove that these are complex, it's trivial. We look at what we've done. This one is done. We're left with this guy, and it uses a plus b minus c equal a minus c plus b, which is a theorem in Metamath, and they're just belonging. We just need to prove that those things belong to C, which is again somewhat trivial. So all in all, nothing quite impressive, but all in all, we were able to generate a pretty large Metamath proof, right? By just pressing enter and Control U, and so that's what is quite kind of exciting. And I think that's really the reason why that 14-year-old student was able to formalize something using Metamath in a couple hours, because it's just pressing enter and stuff, right? But as you formalize more complex things, generally what you'll get is that the model will generally, you'll feel that the model knows where it's going, but will generally get it wrong, but it will give you all the framework that you need to fix the error, which makes the formalization effort much faster. Yeah, that's pretty much it. And I'm happy to answer any question.
Yeah, thank you very much. That's super exciting.
So something I wanted to mention that I noticed about that proof, you know, people will probably look at that and say that this is, you know, something that in Lean this would be like a push button, like a ring tactic would just handle this. But what I want to point out about that proof is that it's a lot smaller than the proof that ring would generate, right? This is much better at generating minimal sequence of rewrite steps that would produce like
Mario, I mean, in Lean you would need to provide the fact that you want ring to prove that a minus b square is a relevant thing.
Right, and writing it as a minus b squared rather than a plus 0 minus b squared or some stupid other thing like that, right? Not only is it generating these witnesses, but it's also actually pretty good at generating them in idiomatic form, and that's something that I don't know that. So I think that a language model particularly would be is pretty good at doing that sort of thing.
So I had a question for you. You said sort of at the end of your talk something. Well, we're just giving it dilemmas. We're not asking it to tell us what to prove. But could you, in principle, could you do that? Could you ask it to make conjectures and either try to prove them itself or offer them to the user?
So actually, there's obviously we can provide. So first, what you can do is you can not condition the generation. So it's been trained on goals, proof steps, generate the proof steps. So you could say generate some goals. And since it's been trained on true goals, it'll actually fit the distribution of true things in Metamath, right? As they exist in the database. So right there, just doing that will conjecture a shit ton of stuff. Whether they're going to be useful is an interesting question. The other interesting way to extract conjectures from the model that are not necessarily useful to us as humans, but useful as conjectures to generate more proof and train on them is that as you run those proof search, in many instances, it's going to generate theorem statements that don't exist in Metamath, right? And so when you submit them to the verifier, the verifier say, nah, it doesn't exist, not true. But if you keep all those conjectures and you try to prove them, you're actually capable of proving quite a lot of them automatically. And so right there, it's also an interesting way to generate data. So in a sense, it could be useful for humans in the formalization process by generating conjectures of lemmas that could be useful to go straight to your proof. And the other thing that has been tremendously useful for, I mean, it's really good for searching the database without actually searching it. It's really generating some statements and sometimes makes mistakes, and it's easy for you to fix. And so it's great for as a formalization interaction loop. But the other thing that has been really useful to me, especially at the beginning when I was really bad at Metamath, is that I was going like, oh, there must be a statement like that in Metamath. So I kind of write the statement and I ask the model to prove it. And what it's going to do is it'll prove it, because my statement isn't exactly the one that is in Metamath, but it'll show me quite the 3 or 4 steps that are required to go from my statement to what is in the database. And that is, for a beginner that is faced with a giant mountain of lemmas and theorems that are unknown to them, is a useful tool to kind of discover it. So I think right now the potential in terms of assistance for new users is really tremendous. It's been really useful to me, at least, and I hope it's going to be useful to Lean users as well.
Sure.
Could you also use the learned value function for goals just to assess conjectures? So if I type a statement and then ask the model whether it thinks this statement is true. I'm not talking about providing a proof. Just
yeah, definitely. Though it comes with a caveat, is that we're really estimating probability of the statements given the model itself, right? We're not, I said, we're not fitting truthness, but generally speaking, in practice, for many statements, it's a useful signal for sure.
okay. And do you understand what kind of goals are good for your model, and what are the things it struggles to prove? Or is it
It struggled to prove a ton of stuff, obviously. I mean, it really shines at generating the glue. There's a lot of glue in Metamath, and the glue is really easy to the model. And then we've really trained it a lot on basic arithmetic stuff. So expanding squares, doing some simple inequalities, doing some negative discriminant-based inequality, all that stuff. And it's exciting to see that we're able to shift the distribution towards something that we feel is useful progressively. But there's still a lot of struggle on exercises and stuff, because Metamath doesn't, and most formal systems, I presume, doesn't have a ton of them. And by not a ton, I mean virtually 0.
So I'm just curious, so how much do you think you're limited by the size of Metamath? So like 38,000, I mean, if you look at Isabelle and Cock, it's probably hundreds of thousands of theorems, right?
Yeah. So it's an interesting question. I think it's you always get benefits from more data, but it's unclear to me whether you get benefits on the distribution you care. So if you're caring about doing formalization, more data for doing formalization is good data, and so doubling your dataset size is important because it'll get you to squeeze much more performance from larger models. So this is really useful. And then if you're targeting mini F2F or IMOs and stuff like that, so you get twice as much formalization data. It'll be useful, but not as much. So we'll still have to find ways to shift that distribution progressively. But we are, sorry, to answer your question more straightforwardly, data is the limiting factor today for sure.
Okay, let's thank Stan. It was another great talk.
Thank you.